Okay, so the first thing we did in class today was go over our double replacement homework. So we have two where we have to do the complete ionics, and then two down at the bottom where we're just going to finish out the double replacement. So the first one, you have cobalt nitrate plus lithium sulfide. And so all double replacements, you are going to take the two metals, so the first two, whether they're metals or not, and just switch them out. So our product is going to end up with lithium with NO3 and cobalt with sulfide. Now the problem is when we make new compounds, we have to consider the charges on the new compounds. So I know that lithium is +1 because it's on group 1, it's always +1, and nitrate is -1, so those just cancel. Now cobalt is going to have a specific charge. And so to determine that charge, we have to go back to our reactant side of cobalt and figure out what the charge was over here. So when it's in words, it will like clearly say cobalt whatever charge. But if you have it in a formula like this, you have to go back to the previous side and backtrack to find the charge. So the way you do that, is you look at your anion, which is nitrate. Nitrate has a -1, but there are two of them. So 2 times -1 makes a -2. So that means that cobalt has to be +2 to balance it out. So that charge of cobalt will transfer to the product side as well with a +2. So now we can continue and finish out our compound. So cobalt is +2, sulfur is always -2 because it's on group 16, so those cancel. Now with double replacement reactions, we have to use our solubility chart. And so the solubility chart tells us that these two are aqueous, I already gave you those. And then remember, if it's soluble, you're going to write aqueous, and soluble, you're going to write solid. So lithium and nitrate both are always aqueous with no exception, so we're going to write AQ. And cobalt is not on the list, but sulfur is. Okay, sulfur is, let me find the list. It's on your PowerPoint if you don't know where this is, if you're at home and you don't have it. It's on your PowerPoint, slide 33. So sulfur is generally insoluble. It does have exceptions, but none of the exceptions are cobalt. So that would mean that this compound, compound of copper 2 sulfide is insoluble, so we write an S. So to determine whether the reaction happens or not, remember your product has to have an S or something that's not AQ. And it does have that right here. So that means the reaction does take place and you form cobalt sulfide. So if the reaction happens, like always, we need to go back and balance the reaction. So I'm going to write down all of my different options. So on the reactant side, I have 2 lithium, so I'm going to put a 2. And I have 1 lithium on the product side. I have 1 cobalt and 1 cobalt, 2 nitrates right here, and 1 nitrate, and then 1 sulfide, 1 sulfide. So to balance this out, we need to put a 2 in the front of Li and nitrate, and that would change both of those to 2, and the reaction is balanced. So this is your answer to A. So for the complete ionic, it says to separate out the aqueous compounds and then leave any solid, liquid, or gas. So what we're going to do is anything that says aqueous, we're going to break it apart into its ions. So we're going to take cobalt with its +2, and we're going to say 2 nitrates with a -1. Now notice that this 2 right here on the subscript applies to the nitrate, and in the complete ionic, we bring that 2 out in front. Okay, lithium sulfide is also aqueous, so we're going to do the same thing. Oops. +1, and then we have an S with a -2. So 2 lithium nitrate right here. This is also aqueous, so we're going to separate those. Now this 2 applies to lithium, but it also applies to nitrate, so we're going to use it for both. Okay, and then the last thing is copper 2 sulfide, which is the solid. So this solid we have to keep together because that's what the instructions say. The complete ionic keeps your solids together. So I'm going to bring that down and make sure you keep that S with it. Okay. The net ionic is where you take out any spectator ions of the complete ionic. A spectator ion is an ion that is found on both sides. So an example would be 2NO3. Do you see how it's exactly the same on either side? Okay, that is a spectator ion, and we are just going to cancel it out and not bring it down to our net because it says cancel out any spectator. Okay, lithium is also a spectator because it's right here, 2Li plus 1, and it looks exactly the same on the product side. So it went in as an ion, it came out as an ion, so it does not count and into our net. The things that do count are the ones that did not go in as an ion and out as an ion. For example, cobalt plus 2, it got trapped into the net because it made a compound. So everything else that's left, the cobalt with the plus 2, the S with the minus 2, the yield sign, COS, and the S, that gets brought down into our net ionic. Okay, so that's everything for number 1. Number 2 is exactly the same way. So I'm just going to speed through that. I did mess something up though. I forgot to put right here, K is always a plus 1 and carbonate's a minus 2. I forgot to put the 2 at the bottom of K. So if you were trying this and you could figure out why it wasn't working, that was probably why. So double replacement, we're just going to switch the metals. So the copper is going to be in front. But remember with copper, I have to have a charge. And you cannot just make this charge up. You have to go back to your reaction, to your reactant, and figure out what copper was on this side so that you can bring it over. So right here, you have acetate as the anion, and acetate is a minus 1. Well, I have 2 of them. So that means I have a minus 2, so copper has to be a plus 2 so that those 2 can balance out. So on the product side, copper is also a plus 2. Okay, let's just clean it up. So copper will come first, and it will be with carbonate this time. And the 2's balance, so I'll mark them out. And then, oops, my potassium is going to go to the end, and it will be with acetate, which has a minus 1, and those charges balance. So since this is double replacement, we have to include our aqueous stuff and like aqueous or solids for solubility. So I know that potassium is always soluble, so this is AQ no matter what. Now copper is not on the solubility chart, but carbonate is, and carbonate is generally insoluble except when it's with lithium, sodium, potassium, or ammonium. None of those are copper, so this would be insoluble, so we put an S. So if we have a reaction, we're going to balance it. These are pretty easy to balance. You have 2 Ks and 2 acetates, but on this side you only have 1 of each, so we're just going to put a 2 in front. Okay, the complete ionic, again, we're going to break anything that's aqueous apart, and we're going to keep the solid together, and we're going to use all the subscripts as coefficients. Okay, remember to bring the solid down. We can't separate it out. All right, so that is our complete ionic. We make our net by going through and canceling out any spectator ions. So K and K, they look the same both places, so I'm going to cancel them. Okay, acetate is the same on both places. I'm going to cancel it. The rest is my net. So I have CO3 minus 2 plus Cu plus 2 yields copper, carbonate, CuCO3 with the S. Okay, the last 2, we do have to write them in words first, and then we can transfer them to their, if they form a reaction, we can transfer it and build it and balance it, all the things that we do. But we don't have to do the ionic ones on these because it doesn't ask for it. So again, this is double replacement because you have compound plus compound. So you're just going to switch the beginning of each. Sorry, ran out of room. Okay, and then we're just going to build it. So silver 1, Ag is silver with a +1 charge. Nitrate is NO3 -1, so those balance. Sodium is Na +1, chloride is Cl -1, and those balance. Sodium nitrate, sodium is Na +1, nitrate is NO3 -1, those balance, and silver 1 chloride, Ag +1 and Cl -1, and those balance. So to determine if the reaction actually happens, we have to look at all the states. We have to determine which ones are aqueous, which ones are solid. So anything with nitrate is going to be aqueous. Anything with sodium is going to be aqueous because they have no exceptions. So the last one to consider is silver 1 chloride. If you look at your solubility list, chloride is generally soluble, so we would think AQ, but the exception is with silver, and when it's with silver, it is insoluble. So for insolubles, we put an S. So this reaction does happen, which means we need to balance it, but everything is 1, 1, 1, 1, 1, 1, 1, 1. So it's already balanced. Okay, next. Potassium chlorate plus sodium sulfate. Again, compound, compound. So we're going to switch the front. Oops. So sodium chlorate and then put potassium at the end. Potassium sulfate. Okay, now I'm going to stop here because if you look at your solubility chart, anything with potassium or sodium is always aqueous. So every single one of these is aqueous. Okay, if everything is aqueous, we did not form anything, so we get no reaction. So that's our answer. All right, that's everything that we did for our homework on double replacement. Also in class, we went to the PowerPoint and we went through this oxidation reduction stuff. So let's go ahead and do that again, whether you're hearing it for the first time or you just needed a refresher in class. Here we go. Sorry, I got a lot to erase. Okay, so oxidation reactions, oxidation reduction. We call these redox reactions for short. So this is just where we are going to follow the electrons as they are transferred from one reactant to another. There are two parts of this. There's an oxidation part and a reduction part, and they will always happen at the same time. They won't happen separately. So these are not a separate group of reactions, okay? This idea, this redox reaction, we are just going to provide an insight into synthesis reactions and single replacements. Those are the only two that we will be considering. They can happen other places as well, but these are the only two we're looking at. So consider the following reaction. 4NaS plus O2G yields 2Na2OS. This is a synthesis reaction, and so is this one. So these are both synthesis, but they also have a redox reaction happening as well. So for redox reactions, we are going to assign one electron as being oxidized, one atom as being oxidized, and another atom will be reduced. The way you can remember what oxidize and what reduce is by remembering the saying, Leo says Gur. So oxidation is the loss of an electron. So lose electron, oxidation. Leo says Gur, gain. If you gain electrons, it is reduction. So if the reduction is the gain of an electron. So if you look at your example right here, I have 2Na plus Cl yields 2NaCl with the charges on them because this is an ionic compound. So we are going to analyze what happened to sodium and what happened to chlorine. So sodium at this point has nothing, right? And then it goes to a +1. So if sodium goes from 0 to +1, that means it lost an electron, meaning an electron came off as the product. That would be oxidation. Chlorine goes from 0 to -1. So it gained an electron, so that would be reduction. Now, I don't ever write mine like this. I don't like the way that's written. I'll show you how I write mine, how I keep up with it. But we first need to learn about oxidation states. So oxidation states are our imaginary charge based on a set of rules. This is kind of our like chart that we can use to follow the flow of electrons. So if the compound is ionic, then the charge is just going to indicate the oxidation state. They will be the same. But when it's not ionic, you have to use this chart to determine what oxidation state each of the atoms have. Now, it's important to realize that oxidation states, they look like charges, but charges are real. An ion charge is real. Oxidation state is just our explanation of where the electrons are trying to go. So it's not necessarily a real number, it's just like a tracking system. So this chart works like a hierarchy. So you start at the top and you work your way down. The first two are for elements that are not in a compound. So an elemental form just means it's sitting by itself. So these are always going to have zero, the same way that I've taught it to you with like ions. And then if it is an atomic ion, that's like if sodium were in a solution and had a +1. Like if the ion is written +1, then you know that the oxidation state is also +1. Okay. The next group right here, these are all for in a compound. Okay. So say we have a compound of NaCl. Okay. We have two things together. So we have to determine the oxidation state of each. We have to work down this list to figure out which element, sodium or chlorine, has priority. Most of the time, like with an ionic compound, when you have metal, non-metal, it's just going to go with the charge, like it'll just make sense. But I'll still show you how to read the chart. And then make sure that since there's no overall charge, like you don't see a number right here with a plus or minus, that means that this compound is considered to be neutral. So these, whatever your oxidation states are, will add up to zero. We just have to figure out which one has priority first, whether sodium or chlorine. So what you do is you consider sodium and chlorine and you work down this chart, ignoring the first two because those aren't compounds. These are for compound. And notice this right here just says neutral compounds add up to zero, ionic compounds add up to their charge. So we have a neutral compound, so we're adding up to zero. So in the compound are either of the elements in group 1. Yes, we have sodium. So sodium gets the priority. We're going to give it a +1 as its oxidation state. Well, then we are not going to look at that chart anymore. We are going to use math to solve for that oxidation state on chlorine. So if sodium is +1, then chlorine has to be -1 for this to add up to 0. Like I said, it makes sense with ions because it just tends to be the charge on like what you would expect the metal or the non-metal to have. So let's look at these oxidation states. Like I have a lot of examples down here. The first one is just chlorine 2, just by itself. This is what we consider elemental form. So this would have a oxidation state of 0. The next one, Na+1, that is what we're talking about with atomic ion, where it's an ion, it's not with anything. Its oxidation state would be +1 as well. The next one is a compound, Kf. So in a compound, remember we have to work down this list and figure out which one has priority and then solve for the overall charge, which is 0. So K is priority because it's on group 1 and that's what comes first. So it says give K a +1, so +1. Well, what does F have to be for this to add up to 0? Well, F needs to be -1, what we expected it to be. Now, it looks a little different when we get something like carbon dioxide because both of these are nonmetals. Okay, so they really don't have a charge because this is not an ionic compound. So our oxidation states are really going to be imaginary because there's no charge because it's not ionic. But we're still going to give it an imaginary oxidation state. So we're going to look at this compound. There's no charge out here, so we're going to assume we're going to add up to 0 for neutral. So we have to determine carbon or oxygen. Which one is higher on this list right here? So we're going to work our way down. Are either of them in group 1? No. Are either of them in group 2? No. Are either of them hydrogen? No. Are either of them oxygen? Yes. Okay. This is a normal compound. It's not a peroxide. So this is going to be a -2 for the oxygen. So that means that oxygen, give myself more room. Sorry, hold on. So that means that our oxidation states have to add up to 0, and oxygen is a -2. Well, I have 2 oxygens, so that is -4. So what does carbon have to be to add up to 0? It has to be +4. So the oxidation state of carbon is +4, and of oxygen is -2. So let's look at this one, our next one. This one is a polyatomic. This is sulfate. Do you see how the charge is indicated, -2? That means that the oxidation state will also add up to -2 instead of 0. So again, if you go down this chart right here, neither one are in group 1, neither one are in group 2, neither one are hydrogen, but we do have oxygen. So we're going to give oxygen its normal -2, but we have 4 of them. So that means that we have a total of -8. Well, now we need to know, what does sulfur need to be for this to add up to -2? Well, that would mean that sulfur has to be a +6. So the oxidation state of sulfur is 6 and of oxygen is -2. Okay, so when we apply this, let me go up here and redo this problem the way I like to do it. I can just give myself more space. Hold on. Okay, so let's take a synthesis of sodium chloride. Na plus Cl2 yields NaCl. Okay, we got to balance it. Okay, so the first thing we realize is this is just a synthesis reaction, but I want to know which element is oxidized, I'm trying to spell, and which element is reduced. So you won't do this to everything. You will only do this very rarely when I ask for oxidized or reduction. So what we're going to do is we need to go assign the oxidation states of every element that's not a polyatomic. Well, we don't have polyatomic, so we're just going to assign it to everything. So according to the chart, let me clear this chart out. An elemental form is when an element is by itself. Well, we have 2 elements that are by itself. We have this one and we have this one. So both of those have an oxidation state of 0. When we get inside a compound, we have to assign priority. So the whole thing's going to add to 0. And on this list, group 1 comes first. So sodium is going to have a +1. So if sodium has +1, that means chlorine has -1 so that they can add up to 0. Okay, so the first thing you do is assign oxidation states to all mono. Anything that's mono, so basically not poly. Anything that's not polyatomic, okay? The second step is to track the difference. So what I mean by that is I use arrows, and so I use an arrow going, okay, sodium changed, so I put an arrow to it. Chlorine also changed, so I draw an arrow, okay? And on top of the arrows, I'm going to track the oxidation states. Sodium went from 0 to +1, and chlorine went from 0 to -1. So I just tracked it. And then my third step is going to be to identify the change as loss or gain. Okay, so if I go from 0 to +1, does that mean I lost or gained an electron? Well, I got more positive, so that means I lost an electron. And according to this mnemonic that I told you to remember, Leo says Ger. If I lose an electron, I'm oxidation. So that means that sodium was oxidized. So oxidized sodium. Okay, and chlorine went from 0 to -1. So that means that chlorine gained an electron, which would mean that it reduced. So chlorine was reduced. Okay, I have another one for us to do together. Mg plus HOH, this is just water. I wrote it differently, of course. We're going to make MgOH2 plus H2, and then to balance it, we need a 2 in front of the water. Okay, so this is a single replacement, but my question to you is which one is oxidized? Which one is, I misspelled that. Which one is reduced? So if I ask you this question, you have to go through all of these steps. So the first thing is to assign oxidation states to all mono. Okay, so since OH is hydroxide on the product side, we are going to treat it as hydroxide on the reactant side, and we will not assign oxidation states to it. But we do have to assign them to everything else. So Mg over here is by itself, so it's 0. Hydrogen on the product is by itself, so it's 0. So the only thing we have to do is hydrogen and magnesium in the compounds, okay? And both of them are going to have priority over that polyatomic. So just give it the charge that it prefers to have, okay? Going through that chart, I did the same thing. Makes sense because I used elemental form for the two that were by themselves, and then for the ones that are in the compound, I went through the priority. Magnesium's in group 2, so it has priority. It gets a +2. And hydrogen's is next, and it has priority of +1 when it's with a nonmetal. And OH these are nonmetals, so it gets +1. Okay, so I assigned oxidation states to anything that was monoatomic. My next step is to track the difference, so I need to draw arrows saying I go from 0 to +2, and I go from +1 to 0. The third step is to identify the changes as loss or gain. Okay, so to go from 0 to +2, that means that I lost electrons because I got more positive. So if you lose electrons, this is oxidized. So which element is oxidized? Magnesium. So that means that hydrogen has to be reduced, but let's prove it. Hydrogen went from +1 to 0, so it got less positive, so that means it gained an electron, which is reduced. So that means that magnesium is oxidized and hydrogen is reduced. All right, good news is we'll only have like 2 questions on any of this material, 2 to 3 questions on your test. So I realize that you're not going to understand it fully. I just want you to be able to do something something similar to what I did on this page right here. The only thing else we went over in class is neutralization, which is really easy compared to oxidation reduction, because this is just basically a double replacement reaction. So a neutralization reaction is when you take an acid and you add it to a base, but really this is just compound plus compound. So we're going to switch the front two, okay? So what you're learning new is that a base is a metal hydroxide, okay? An acid we already knew was H nonmetal. A base is metal OH. So a neutralization reaction will always end in salt and water, but this is obvious when you look at it like a double replacement. So if you switch your metal and your H, the metal comes in front of the nonmetal, which makes this an ionic compound, which is a salt. If the H goes where the metal is, you get HOH, which is water. Okay? Now I wrote it all out. I wrote the complete ionic and I wrote the net ionic. So your acid and your base are both aqueous. Your salt is aqueous, but water can't be aqueous. Okay, it's just going to be a liquid. So this is what we actually formed. So that's what our net is going to show us, is that we just formed water. Okay, take a look at this summary page. We are done learning new material for this term, for this unit. So next class will be a review, and then we will take our test the next class.